All right, hello. Yeah. Yeah, okay, so first question is, what will be and won't be on the quiz? So, I posted on Piazza a list of topics, so last night I finally got to see the quiz. So, I went through it, I deleted all the stuff that we haven't covered yet, so there's no surprises where you have to go look at his lecture notes or something like that. I also posted on Piazza a list of topics you don't need to know. Just to be clear, it's like you don't need to understand how to use fork, exec, join, all of that, or wait, because they haven't learned it, right? I could ask lots of questions about that, but they don't know how to do it, so can't ask it on the quiz. You don't need to know about zombie and orphan processes, because you'd have to create processes for that, right? You don't need to know about joinable and detached threads. You should, however, know that threads can execute if they're preemptible in any order, and then there's cooperative threads, which is like lab 2, that you have to explicitly yield, and we'll talk about that a bit more today. You don't need to know anything about that add exit stuff. You don't need to know like any specific assembly. You don't need to know about the MMU. You don't need to know about C calling conventions. So if you kind of break down everything, quiz 1's actually really, really easy. like if I can't ask anything about creating processes or managing processes, that means lecture 4 won't be on it. Lecture 5 won't be on it. They haven't done IPC, so lecture 6 isn't on it until the very end, which is like the exception thing, and then polling versus interrupts. Yeah. So they talked a little bit about MMU and talked about processes and threads, but they went into more like low-level detail that's covered in the lab that you'll be doing in the lab anyways. So I thought it was better to just see how things actually work and kind of combine the Unix calls and when we learn about it. So we already know it. Yeah. Yeah. What, post on the Discord about the thing? About the topics? I put on Piazza, not Discord. I can put it on there too. But yeah, so there's a list of topics on Piazza. The quiz is pretty easy. It's like 3 short answer questions are like max 3 sentences. Then there's just multiple choice, true, false, and multiple answer where you can select multiple things that apply. It's honestly pretty easy. You shouldn't be that worried about it, especially because like half the stuff I talked about isn't even valid to ask, right? So I think Ashton said he'd post like a mini quiz of like 5 questions just to give you a taste of it. But honestly, it's pretty easy. Like I would say worry about like lab 1. I was worried about that for you, and lab 1 was kind of bad. This is not lab 1. Like you'll see after the quiz, it's not that bad. It's just unfortunate that I think this is the second time it was offered like that, so there's really nothing to study for. But really, if you distill the content, we know, and they know, how many questions can we even really ask? Like, even if I gave you an example of a short answer question, it's likely that it would just be on the quiz, and I'd be telling you what's on the quiz. So I don't even know if I can give you an example of a short answer. 3 short answer, and then, I don't know, a handful of other ones. Yeah. Can you give me an example of a short answer?
What's your student number?
That's only 1 sentence. 2 or 3 sentences. So like, they know conceptually what processes are. You should know that too, what they encapsulate, at least virtual CPUs and are their own address space. And threads are like virtual CPUs. With that, you can ask some questions. You can compare and contrast. That's always a popular thing to ask. You can, I don't know, say what's different about them. Remember, we accessed the same memory in 2 different processes, and it was different. That was kind of cool. You should be able to say why. Like, yeah, feel free to ask me stuff. I'll kind of blast through this lecture, and then we can ask general questions and just screw around. Yeah.
Like online quiz or like past years, it's like a paper?
No, so it's, oh yeah, so it's just an online quiz on Quarkus. A lot of students are like, oh yeah, I don't know a good place on campus to get it. So what we think we're going to do is we're going to book a room from 8 to 9 and I will be there. So we'll just have a big room so everyone will have internet, or if everyone's internet goes out, at least you will have a witness to it if the campus network goes out. So I can be like, hey, everyone that was writing in my room got screwed. So we'll offer that.
Is it optional or we have to?
It's optional. You can, of course, just go home and do it or go somewhere else. But there'll be a big room so you know that there'll be a spot for you. And I will be there. I, of course, can't answer any questions, but I will be there for moral support. Yeah. You can bring whatever you want. Yeah, quiz is open whatever, because it's not like, I mean, you could write it at home. It's not like I'm going to be like, hey, everyone, connect to the Zoom call so I can watch you creepily write this. Like, that's one, kind of an invasion of privacy, and two, just kind of weird. All right, so let's just kind of blast through today's lecture, and then we can get to, we can hypothesize some questions if we want. And then next lecture, nothing will be on the quiz, and we might go over some review stuff. Yeah.
Just to confirm, so you mentioned everything from lecture 4, 5, 6 will not be tested, or?
So lecture 4 was creating processes, all about fork and the parent-child relationship. They don't know anything about that. All they know is that you can create new processes somehow through magic. That's it. 5, that's process management. You have to know how to create a process to be able to manage it. So 5 is completely not on it. And then 6 is they didn't do IPC. You should know like read, write, and open maybe, but not really. And then like pulling versus interrupts, and then the 3 exception classes on the CPU. That's the only thing from lecture 6. Yeah. No, I don't think they really know about file descriptors. Yeah, and luckily for you guys too, I accidentally told the other class that the quiz won't contain anything from the lab. So I think Ashwin wanted to put some questions on there, but because I accidentally said that they wouldn't be there, so you don't have to answer those questions.
Wait, there's nothing from the lab either?
Nope.
Oh.
Yeah. And you're welcome. I accidentally said that, so I just deleted everything. All right, so let's quickly just go through today's lecture. The first part of it may or may not help with the quiz. So data races and that would not be on the quiz, but arguing about threads and what order they execute would be on the quiz, or would be valid. So this will be important later on because data races are kind of the bane of your existence when you have to program concurrently. So it's good to know the definition of a data race. So a data race is when there are 2 concurrent actions or accesses to the same variable, so same memory location, so same variable, and at least one of them is a write. So if one thread is reading, and the other thread just writes, that can also just show, or that can manifest in a data race where you get results that you would not expect. And data races are bad. So when we did that count example, we had count, that was a global variable. We had multiple threads accessing it. They were all reading and writing it. And that's why we got some inconsistent results. And we'll break it down even further today just to make it really clear why we had some weird results. So first we have to talk about atomic operations, and they are indivisible operations. So anytime you see an atomic operation, you know it either has not executed yet or it has executed to completion. There's no middle ground, right? Plus plus count is actually a bunch of operations. It is not atomic, but it consists of atomic operations that it could context switch out of in the middle of it. So any atomic instruction, again, happens all at once, or it either happens or it doesn't happen, no in between. So that means you can't preempt in the middle of the instruction. If you preempt, either it has happened or it hasn't happened. So between 2 atomic instructions, of course, you can get preempted. So that's all we need to know about that. And then there's this thing called 3-address code. If you get into compilers, it's really, really fun. Compilers are great. Hopefully I might teach that later. But 3-address code is something that is used internally in compilers to kind of argue about optimizations without having to read assembly, because assembly kind of sucks. So basically it just simplifies everything for you. So your program is just represented by simple statements, and they all represent one just fundamental operation, and you can assume each statement is atomic. So it makes it real easy to use or reason about data races, and it's way easier to read than assembly. So because everything looks like this, it's just a result, right? Some variable name or something like that equals one operand, operator, another operand. So 1 plus 2, or there may not even be an operator, there may not even be another operand, right? That's as complicated as it gets. So x equals 1 plus 2 is the most complex this will get. So Jimple is the 3-address code used by GCC, the compiler that you've probably all been using so far. This, again, will never be covered in the quiz. This is more for your own interest's sake. So if you want to see the Jimple representation, you can use that flag. You can see all of the 3-address code generated by the compiler if you want. And it's kind of easier to reason about, again, like I said, than just low-level assembly. So we'll look at that data race example we saw last lecture and see the Jimple code for that. So just to make it really clear that count's a global variable and it's in memory, I turned it into a pointer. So pcount is just the pointer to that global address that represents the count, right? So if you look at the Jimple of plus plus count, you can see it's actually 3 operations. So the first operation here is our load. So it will load dereference pcount from memory. So basically just read in whatever value it's pointing to from memory. And then this is just a temporary, you can think its abstraction is that it assumes that you just have a machine with an infinite number of registers. So D1 is just some temporary storage, and since it's a register and this is executing on a thread, it's independent to that thread. So then the next statement is our actual increment, which would happen just in that thread. So it's just creating, assigning a new register to the value we just read from that memory location, which was D1, and then adding 1 to it. And then in the last step, it just writes out that value. All right, that's our write. So let's see all the possibilities here. So this is a good thing to reason about, all of our possibilities. So if I write them down, the only thing I really care about is accesses to the same variable, in which case it's whatever pcount's pointing to. So I don't really need to label the increment because that's local to the thread. I don't really care. So I'll just label the read and write because they are the important things. And then just assume we have 2 threads and all they do is execute those statements once. And of course, within a thread, threads are just like everything we're used to. They will execute sequentially. But since we have 2 threads, what can we say about what thread executes first? You don't know, right? So if you want to argue about data races, you have to consider all possibilities, which you can see how this gets kind of hairy quick. So one possibility might be that, hey, well, my first operation is a read, so maybe I'll just pick thread 1 to go first. So if thread 1 goes first, it would do this. It would read from memory, which initially here, pcount is 0, right? So it would read 0. So that's all it would do. And now, at this point, you don't know what's going to happen. That was an atomic operation, so now that atomic operation's done. So now there's essentially 2 possibilities. It could execute the next instruction, or because we're going to assume a preemptive scheduler, it could just get preempted at any time and then switch over to the other thread. So if it switches over to the other thread, say we get unlucky, it would do the memory read again, which pcount is still 0, and it would read the value 0. Now, at this case, we're kind of screwed. It doesn't matter. So say Thread 2 just executes the increment. So we would have D2 equals to whatever it just read, 0 plus 1. So D2 would be equal to 1, right? And now, again, we don't know what would happen. It could switch back to the first thread, in which case it would execute its version of this. And it read 0 into D1, so it would be 0 plus 1 equal 1. Now at this point, it also doesn't matter, so it would write out pcount equal to 1, and then it could, then at this point, if we assume the thread's done at this point, it would switch back to thread 2, and then also execute pcount equals to 1. Right? Any questions about that? Yep.
What did you mean by preempt?
By preempt, so there's two types of thread scheduling, right? There's the cooperative one, where you have to call yield to give up the CPU. And then with preemptible scheduling, it can be just taken away from you at any point, and you have no control over it. So that's, and remember we talked about that when we talked about processes too. So cooperative versus like true multitasking or preemptive, which basically means it's just taken away from you, and that's, you know, valid for the quiz. How would an operating system be able to take away the CPU from you?
So
Right.
two ways. One is cooperative, that is the thread or process calls that, or it can be preemptive.
Yeah, so in cooperative threading or process scheduling, you have to yield the CPU to something, and preemptive is just taken away from you. You have no choice. The operating system maintains control, and the operating system would maintain control over processes because it can interrupt itself. Essentially, it has access to the hardware, while your process doesn't, because, you know, clear separation of kernel space and user space, which is all good stuff. All right, any questions about this? All right. Well, so in the case of, so if we got slightly luckier, whoops. So if we got slightly luckier, the normal execution, if we just execute thread 1 all together, it would do something like this. So then next step would be to write out pcount, which would be 1. And now at this point, if it context switches back over to thread 2, it would read pcount into its, you know, its register, which would actually be 1 in this case. So then D2 would actually increment 1 plus 1 equals 2. And then we would get the correct answer, right? So that's kind of what we would expect to see. But you'd have to argue about every single interleaving. So if you do all the interleavings, well, for the first thing that executes, assuming we have 2 threads, either the read from thread 1 can happen first, or the read from thread 2 can happen first, right? And then there's 2 options of what happens after the read from thread 1. Either it could execute its next instruction, and we'll just assume the increment doesn't really matter. We'll just concern ourselves with the reads and writes. It could either execute its next instruction or get preempted and do the other thread. So if it executes its next instruction, it would execute write 1. But if after the read and thread 1 it got preempted, then thread 2 would read, right? And then going along this path here to the right, if thread 1 writes, there's only one option, so you can just thread 1 is done at that point, so there's only one option. You can read from thread 2, or you can write, then you would have to write to thread 2. But after the read, there's 2 options, either because at this point, after the read of thread 2, we can assume we're executing thread 2. It would either continue executing thread 2 and do a write 2, or it would context switch back and do a write 1. And then in either case, after the write 1 would be a write 2, and then after the write 2 would be a write 1, right? So those are all your options if you start with read 1, if we are just arguing about that memory address, right? So any questions about all those interleavings? anyone see how this can get out of hand really quick if you have like 8 threads and you're doing multiple variables, right? So it gets real hairy real fast. And again, these are why bugs like this kind of persist for 7 years. So if we go through all of our orderings, which again, we're assuming that the compiler won't reorganize won't execute out of order or anything silly like that, which actually may happen, which complicates your life even further, but we'll be nice and say that the compiler and the CPU itself won't reorder anything. So if you can't reorder the instructions within a thread, it'll always read, then write. These are all our possible orderings, and we'd see that we only get the result we expect in 2 cases. So if it's equally likely to preempt at any, after any atomic instruction, the odds aren't in our favor that we'll get the correct answer, right? So if this was used to like calculate your grade or something, you wouldn't want to use this code because it's just going to be lower. All right, so let's see how to combat this. So this will be used later. This is definitely not on the quiz, but it's a good thing to know. So to prevent data races, the simplest mechanism to do that with is called a mutex. And a lot of this is just for reference. You can either create them statically, like this, essentially to just create a global variable for them, and you have to initialize them like that. Or you can just allocate them dynamically by calling pthread mutex init, which internally you can think of as just doing the malloc call and some initialization for you. So because we're all good programmers, we know we should free our memory. So you would have to call pthread mutex destroy on it, and that essentially is free. And then if you want to include attributes, it kind of looks like the pthread stuff. You'd have to use the dynamic version, but that's just for reference. You can just use mutexes. Yeah.
So for both way of initialization, we need to destroy at the end.
So if it's initialized globally like this, you don't have to destroy at the end because it's a global variable, so you can't destroy it. It just exists as long as the program exists, or the process exists.
But why there is pthread mutex destroy everyone?
So destroy is to pair with a init. So it's similar to how just variables work, right? If I call malloc, I should call free, but I don't have to malloc every single thing.
Yeah,
Right.
but my question is why there is a pthread mutex destroy for everyone?
Oh.
I didn't call init.
So this isn't the same block of code, it's just multiple examples. Yeah. Okay, so this is the important bit this is how you typically use locks. So you have some code you write, and then you call pthread mutex lock, and then within that protected code is also called a critical section, which has some unique properties. So everything between the lock and unlock, only one thread can execute it at a time, and that is the purpose of a mutex. It guarantees mutual exclusion, so only one thread can execute that at a time. And if only one thread can execute that protected code or be in that critical section at a given time, we suddenly don't have data races because we can't have 2 concurrent accesses if only one thread can be in there at a time. So everything within the lock and unlock is protected, and you have to be careful to avoid deadlocks, especially if you use multiple mutexes, which we'll see later, but for now we'll just assume a single mutex. And also, so lock is also kind of a blocking call. We'll see its implementation in the next lecture. But if one thread makes it there, gets the lock, and another thread tries to get the lock, it will just sit there and wait until the lock is unlocked, and then it can grab it again. If you don't want to block, you can use this function called try-lock, which you probably won't need. It might come up later, though. And the lock is just how you would expect a normal lock in your everyday life. When you create one, it's initially unlocked, and then you just lock and unlock it, and you can't lock it twice in a row, and you can't unlock it multiple times. Yeah.
Sorry, what's a deadlock?
So deadlock is basically when you can't make any progress. So if you forgot an unlock, so if you just locked something, and then you forgot to unlock it, and then another thread tried to acquire that lock, it would just sit there forever because nothing is ever going to unlock it. And deadlock is just basically you get stuck at a lock call, you can't make any progress, you can't move anymore.
So
Yeah.
you first lock it, then you do something before you unlock it? Or?
Yeah, so between the lock and unlock, the code here in the critical section, protected code, only one thread can be executing that at a time. So if that's our only accesses to some global variable or that have a data race, we now eliminated our condition for a data race because it was concurrent accesses, right, to the same memory location. But between lock and unlock, there's going to be no concurrency there because only one thread can execute at a time. So if anything context switched over to it, it wouldn't make it past the lock, it can't execute it.
And it's only supportive in mutex, not a normal pthread.
Yeah, so it's just a mutex. So mutex is just a type of lock, and pthread is just the actual thread. It's just locks and threads are related, so it's in the same library, so it's just called pthread at the beginning. But they could have been nicer and just called it mutex lock or something. But it's in the pthread library, and C is kind of terrible, so they have to name it something unique. So this is our data race example we saw before. So in order to prevent the data race, right, we just create a lock at the top of our code. It's essentially a global variable, so we can initialize it like that. We could destroy it, but you don't really need to destroy it. It just makes it invalid, but it doesn't free any memory or anything like that. And then within here, so within the loop, we'd have our lock call, and then we'd do our ++ counter, and then unlock. So now only one thread can execute that ++ count, that increment at a time, so we don't have any data races anymore. So if we go ahead and look at that, right, so here's our code. We have a lock and unlock. If we compile it and run it, now because there's no data races, we should get what we expect, right? We should get 80,000 every single time, in which case, you know, I can execute it a bunch of times, get 80,000 pretty much every time. With these data races stuff, you can't be, you know, just because you ran it 1,000 times and it worked doesn't mean it's actually right, but we can actually see the code there that counter is where our data race is. Now it's in a critical section. Only one thread can be there at a time, so we don't have any data race, and we can argue about that. Yep.
So, okay, so for like the data race, you said that if you run it 1,000 times, you still can't like verify that it's working properly. But like in this case, you ran it like a couple times, and you can say that it's working properly.
Yeah.
In the case, like I get like, because there's a blatant lock like right there.
Yeah.
But just in general, like if you have like a larger piece of code, how can you verify that there are no race conditions?
Yeah, so that's like still an active area of research to verify that, because these bugs still exist. Like people are still finding new ones, and they've lasted for 7 years, 8 years, stuff like that. Like some stuff you have a data race, but it just never happens because that's the way the hardware works. It just never happens, and then suddenly some new hardware comes out that has some optimization that changes something, and now that's no longer true, and because it actually had a data race before, now you see it. Yeah.
So this would execute one thread at a time.
Yeah, so that is the kind of crux of this, is that now, because between the critical section, only one thread can be there at a time, I essentially turn, this code is now just a really convoluted serial version, right? Because only one thread can execute at a single time.
Yeah, so what's the difference between like just call and run like 8 times or 80,000?
Yeah, so in this case, because each thread, essentially all of its work is in a critical section, then yeah, it'd be easier just to get rid of the whole lock, because it's going to take time to do the lock and unlock. So I would just do it single-threadedly, right? So that's what you would do. But this is just kind of to illustrate the example. Yeah, but in real life, right, that's one of the things you have to consider of, you know, is it even worth doing this operation on multiple threads? If, you know, there's some dependency or something, and I have to make it single-threaded anyways, then, right? Yeah.
In such cases, instead of using shared memory, I just create its own counter variable in the function. The problem is like every
Yeah.
So like after, let's say, executing the counting process and return it, I will add it in the main function.
Yeah, so that's,
To resolve each query.
yeah, so that's a good point. Even if you bear with this silly example, one thing you could do to make this actually run in parallel and do it without the lock is you could just have a local counter in the run of here, increment it, it's 10,000 times, and then pass it as a return value, and then have the main thread just kind of combine all of them, sum all of the threads up together, and then you'd get your answer. You wouldn't have to deal with a lock. So that's one of the things you can do and is a perfectly valid technique, and you just have to weigh the pros and cons with doing all of that. Yep.
So how does Mutex know which thread to serve? Is that like based on the first come, first serve basis?
Yeah, so the question is, how does lock know what thread to serve? And it's atomic. It's just this, if they both arrive at essentially the same time, just one will pass. And even if it's in parallel, because the lock will probably be implemented in some memory location, something, and you'll need hardware support for that, which we'll talk about in the next lecture. The hardware will go ahead and do all the hard stuff for you and just pick one. Yeah. Yeah, so So in this case now, if I go back to my example, so now in the example, if we have a lock, so if our lock works properly and our first call here is a lock call here, so it would have to execute lock, right? We had lock and then our increment and then our unlock. So thread 1, if it gets picked to run first, would first do a lock, and the lock's initially unlocked, so it would pass through and be able to acquire the lock and execute the next instruction. So now it would be running, it would do that memory read. And now if we get unlucky and we get preempted, the other thread is going to try the lock call. And because this is a properly implemented mutex, it's just going to sit there. It's either going to yield the CPU or put itself to sleep because the other thread has a lock. So it's not going to be able to execute that memory read anymore. It's just going to stay here, do whatever, and then eventually either it will yield, it will put itself to sleep, or it will just time out and just waste a bunch of time trying to acquire the lock over and over again. But at any rate, at some point, it's going to give up, and then it will context switch back over to the thread that acquired the lock, and then it would go ahead and do its increment. So 0 plus 1. And then even if it context switched back over again, right, it would still be in that lock call over and over again, and it's not going to make any progress. And then eventually it would context switch back over to thread 1, and then it would it would write out pcount equal to 1, and then finally unlock. And then after it unlocks, then it would pass through the lock and acquire the lock now. And then it would go ahead and read, it would go ahead and read that memory location, which has now been updated. So it would read 1, and then it would execute what it should. 1 plus 1 equals 2, and then write out pcount. Yeah, so does everyone see how that works, right? Anytime it context switch over, it'll be stuck in that lock call, won't be able to make progress, so then we don't have a data race. And I guess to translate it to kind of the cooperative threading issue. So if instead, we just had our code as before, but it was a cooperative thread, and we had something like this, do we have a data race now?
Yes.
We got a yes and a no. Why yes?
Because it's possible to thread having do plus counter then yield at the same time.
So his comment was, it's possible that two threads doing plus count at the same time yield at the same time. So yeah, so you'd still have an issue as long as this was on multiple kernel threads and they could run in parallel, right? They could still be both doing plus count. But if you have a single CPU, this would not have a data race, right? Because it would do plus count, and the only time it can context switch over to another thread is by calling yield. So it would either, then you can think of the three operations plus counter as being kind of atomic, but not really. They're not really atomic. They either all three happen, and then I yield, or I haven't executed them, or I'm executing, so I'm about to execute them, right? Yeah.
What happens if you have, like, you have this run here and unlock and unlock, but let's say you have run 2 or something with that is just normal, no unlock, no lock, and no unlock, and 4 of the threads are run, the other 4 are run 2. That would still have your CPU.
Yeah, so the question is if I just, say I just copy pasted this. I gave it the name run2, and I did that, right? I did that, and then when I created it, let's just say, else. So you want something like that. So essentially make half the threads use the lock and the other half the threads not use the lock. Well, let's just see. Right. So there's still a data race then, because even though there might not be a data race between the 4 threads that use the lock and unlock, our definition of a data race is 2 concurrent accesses to the same memory location. So you can guarantee within 4 threads there's no concurrent accesses, but there's some other threads that will access it. So you still have a data race. I guess you can argue that the number is not as bad, right? Because we have 4 of them cooperating together and being a little bit nicer. So it's slightly better, but it's still a data race. Okay. All right. So let's quickly wrap it up. So these are kind of things you want as properties in your critical section. It means only one thread executes. So if you actually implement mutexes yourself, these are properties you want. You want safety, aka mutual exclusion. So if you implement a mutex, you only want a single thread in the critical section at one time, which means if 2 threads can call lock and pass through, your mutex does not work. You also want liveness. So if multiple threads reach the critical section, essentially they reach that lock call. You want one to proceed. Otherwise, if they all make it there and then just get stuck at the lock call, they won't make any progress and your program won't work. So, and then as part of that, you don't want your critical section also depend on outside threads. They can mess up in deadlock, and we'll see deadlocks in a few lectures. Also, you want bounded waiting, aka starvation free, where a waiting thread must eventually get the lock. It just won't stay there forever. So one of the good points brought up is that we essentially turned our example into a single threaded. So if you use critical sections, you're essentially turning some things that might be able to be done in parallel into sequential operations. So if you want things to run as fast as possible, you want critical sections to have minimal overhead, and you want them to consume as little resources as possible while waiting. You want to make them as small as possible too, right? Otherwise, we're just turning our program into some sequential thing. You also want the locks to be fair, so you want each thread, if they make it there at the same time, to wait approximately the same time. You don't want one thread just skipped over 1,000 times. And you want your locks all to be like simple, easy to use, hard to misuse, which is definitely something easier to say than it is to do. So similar to libraries, you want kind of layers of synchronization. You build them up on top of each other. So at the bottom, there's going to be some hardware-provided low-level atomic operations that you can build on, and we'll see what they are in the next lecture. And then on top of these hardware-provided low-level operations, you can build high-level synchronization primitives. So that's where mutexes would be, and other synchronization tools that we'll see later on. And then on top of that, you use a combination of mutexes and other things we'll see to build your properly synchronized application that doesn't have any data races and works flawlessly. So this is one instance of a lock implementation if you have a uniprocessor system, so just one CPU core. And if the only source of concurrency in that case is interrupts, well, then you can implement a lock by just disabling interrupts. So if interrupts are your only source of concurrency and you disable them, then you just eliminated concurrency and you're the only thread that can run because you can't get interrupted, right? And then the unlock call would just be to enable interrupts again, and now concurrency can happen. But this obviously isn't going to work if you have more than one CPU core, because the other one would be able to run in parallel or concurrently. And of course, because interrupts are a hardware thing on your CPU, if you're writing a normal process, the operating system will not allow you to turn off interrupts because that's its domain. So the operating system wouldn't let you change it anyways, but if you are the kernel and you have a single CPU, you could implement locks like this. Yeah.
Is this only for preemptive? So the thread can still call yield to do concurrency?
So this is just processes or threads, any execution. So not even specific to threads. Whoops. Yeah. Yeah, so this is just concurrency, just executing some instructions. Doesn't have to represent a thread process. It could be operating system code. It could be kernel code.
But still, the mode is not preemptive. So cooperative can still work. So even if you put a process to sleep.
So these interrupts would be from hardware. So you can't control when they come in, right? So there's no cooperative interrupts with hardware.
Yeah.
It just happens, right? All right, so let's try our best to implement a lock in software without any help. So I will create a lock and just represent it as an integer. I'll just choose values. I'll say if it's 0, I'll say that represents it's unlocked. If it's 1, I'll say that means it's locked. So if I want to initialize my lock, I'll just set that value to 0. And within lock, some implementation I think of is I'll just loop infinitely while that lock is equal to 0, or I'll loop infinitely while that lock is equal to 1, because that means it's locked, so I should just try again. Of course, I'm going to waste a bunch of time here, but I'll just try it over and over again. And then if I break out of this while loop, then I know that the lock, or the value of the lock is 0, so I can go ahead and change it to 1. And then that indicates I'm locked, so then when another thread comes in here, it should just hit the while loop and keep on looping again and again. And then to unlock, I'll just change that value back to 0. So anyone see an issue with this implementation if I'm even using 2 threads? Yeah.
The last thread will be deadlocked.
Which thread?
Because no thread, it's the last thread.
Wait. Yeah, okay, we got back there. Yeah.
Maybe because the while other one's 1, it's just wasting time. It's not like doing.
So it's wasting time, but so let's go ahead and kind of argue about it. So let's argue about even 2 threads. So if I have thread 1 and then thread 2, and then say initially, initially the value of the lock is equal to 0, right? So say both of these threads are going to call lock. So if both the threads call lock, you'd expect one to make it past and the other to get stuck in that loop essentially, right? So looking at our lock code, which looks like lock, essentially looks like while L equals 1, then I loop forever, and then when I acquire it, I set its value to 1, right? So if thread 1 gets the lock, let's label our reads. So this is a read. I'm reading the value of the lock, and this line is a write, and that's the same location, right? So if thread 1, we'll just say thread 1 executes first, it would read, and it would get L equal to 0, because that's what it is initially, right? So then if it's still executing, it would go ahead and pass through the while loop, right? It would just go from the read, and it would be there as its next instruction, and then if it executes the next instruction, it would write out that value of the lock is now equal to 1. And now and then it would just return, right? Return from lock. Now if thread 2 chooses to execute, it would read, and it would read the value of L as being 1, and then it would get stuck in that loop, which is what we want, right? We want just to get stuck there, which is fine because thread 1 gets to return from lock, the other thread doesn't get to return from lock. So only one thread made it through that lock call. Yeah.
Is the problem that you can get preempted in between reading lock and 0 and writing it as 1?
Yeah, so that's the crux of the issue. So if instead, before that write happened, I got preempted right after that, then what would happen is thread 2, because that value hasn't been written yet, thread 2 would go ahead and then also read the value of the lock is equal to 0. And now at that point, you're screwed, right? So now both thread 1 and thread 2 are at this point where they'll just break out of the while loop because they read that into some register or something, so it's local. They both see that as being 0. So they would both not get into that while loop, and then they would both return. So 2 threads call lock, and then 2 threads pass through lock, in which case it was completely useless, right? The lock didn't do anything, so this, of course, is not a valid implementation of a lock. So it's not safe. Both threads can be in the critical section. We can argue, it's not safe. Both threads can be in the critical section, and we can argue about a interleaving of threads that cause them both to return from lock. And it's also not efficient because if one thread, gets switched back there, it just pulls over and over and over and over again when it knows, when it should know it can't make any progress. So it's just wasting CPU cycles, which is called a busy wait. All right, any last minute things about the quiz that we can think of or questions? Nothing?
Could you give an example?
Can you give an example? Yeah, the quiz, honestly, the quiz is not bad at all. If next week you can say, next week let me know, either good job you didn't lie to us or I hate you and I'm never coming back. So hopefully you come back. All right, well, I'm pulling for you.